Bismillah ar-Rahman ar-Rahim. Yes, hello everyone. This is Dr. Bassam Al-Hamid with you. So we are going to be talking today about our main design project, and this is part of our process control design project. As part of the process control design project, PICENG422, and you're expected to design the control system of a Tennessee Eastman challenge problem. Okay, so this is the problem that we have, and actually what I'm going to do today, I'm going to explain to you the whole the plant and what are the stages of control that you need to do, and the Simulink file that is going to be supplied to you so that you can use it to control the system. Okay, so we'll take it step by step. Okay, so the Tennessee Eastman challenge problem. So what do we have here? We have a plant, which is the Tennessee Eastman plant, that you need to control. Okay, so what do you need to do? You need to control this plant. So what is this plant? Just a quick glimpse of what we are trying to show you here is that, well, you have three inputs, which are the feeds. Okay, the feed that enter the reactor, and after the reaction, and it's an exothermic reaction, so you need cooling. This is cold water supply, and you have cold water getting in and out. Okay, so after you have your reaction, you have products and byproducts. And because you have byproducts, you want to go through some kind of condensation and separation so that you can get rid of the byproducts and you get a pure product. And even though that you get a pure product, you want to do some kind of stripping if there are still some kind of byproducts so that you can get rid of them and they are back to the reaction. And you have purely the product coming out here, and it goes as a product. Okay, so this is the system. So what do you have here? You have reactor, you have a condenser, you have a separator and a stripper, which also acts as a separation process, and you have a compressor here because you have the reaction is at a certain temperature and pressure. And because it is at a certain temperature and pressure, you would expect that there is a drop of pressure because of the condensation, because of this long tubes, because of the separation. I mean, there's a lot of drop of pressure here. It just comes in because of the drop off of pressure. You have vapor and liquid. And that vapor, it needs to be pressurized through a compressor, so then it goes back to the system here. And what do we else we have? We also have purge. Why? Because within our system here we have inert, and this inert just builds up within the whole system, right? So what we have as in here, feed, goes as a product out here. However, the inert which gets inside here never leaves the system. So the way how to get rid of the system, which would take space with time, which will take space of those separator and reactor, you need to get rid of it through the purge. So that is the idea. Now the question is that, what do you need to control? What do you need to control? We need to control several issues here, or several process variables. Well, I would expect the feed here could be changing, so I may need a feed controller here. I also have the temperature is very important for my reactor, so I need to control the temperature. What else? I have a level because of the decondensation process, so I need to control the level here. Actually, I also have level within the reactor here because of the feed in, so I need also to do some kind of reaction here, to do some kind of a control. What else do I have? So what else do I have? I also have the pressure here is important. So is pressure is important for the reaction, or it is important so that it does not develop and it does not increase to a level that as it accumulates, it may cause this pressure to be too high for the reactor to withstand, and it's like a balloon which blasts, and this thing will blast. Balloon will blast is something very easy to say, but talking about reactor that will blast, that is a disaster. Okay, so we may need to do some kind of something here, like a control or a measurement. So you need to think about it. We have a stirrer as well. Do you want to control the stirrer? Usually the stirrer is kept at a certain point for good mixing, and that is good enough. Do you want to control that? That depends on you. You have the level here we may not need to control. Do you need to control the temperature here for the condensation process to happen at a certain rate? The answer could be yes or no. Well, we have level controller in this condenser, and we may have also temperature controller of this condenser. If we want to control two process variables and I have only one manipulated variable here, what should I do? Should I cancel just one of those process variables and say that I don't need to control the temperature, or should I say that, well, I'm going to do some kind of a cascade over the level of the temperature, or the temperature of the level, which one is going to be master and which one is going to be the slave. Okay, so all of this is going to be part of your study, and then you're going to have the liquid getting in here, and then the separation process. The separation process happens. Do you want to control the temperature here? Okay, so and then the liquid goes in here to the stripper. There's also some kind of level indicator which indicates for you that level control here is important. And do I want to control the level here depending on how much reboiling that I have, or it has nothing to do with this? I'm going to control the level with the output flow rate. Well, I also have the control the temperature here to cause the stripping part for the gas which goes back to the system. So if I want to control the temperature here, would I want to control the temperature using the steam that is used as a reboiler for the gases that are reboiled back to the system or not? That is possible. Or is there a recycle ratio that I want to have between what I'm getting out and what is reboiling, or there's no recycle ratio that I want to use here? And then you have the product. Is there a certain percentage of a product, and the product is G and H here? So is there a certain percentage that I want to sell of having a certain percentage of G and H? And there are three configurations that you are targeting here: 90, 10, 10, 90, and 50, 50. So you're going to control the system based on these three different configurations. So what are the feeds? A, D, E, C. What is the product? G and H. Okay. What we are purging? We are purging everything. What we are realizing here, we have an analysis of all this. However, the most important is G and H. Okay, so this is the system that I have here. That is the system that I do have here, and we are going to rely on the paper by Dons and Vogel. So we are going to refer to that paper. It is the main paper that you're going to use. However, there are two other very important papers that I'm also going to supply you with that you need to read to be able to control the system. So we have here the Tennessee Eastman Plantwide Industrial Process Control proposed by Dons and Vogel as a challenge test problem. And we need to do what? For a number of control related topics, including multivariable control design, optimization, adaptive and predictive control, nonlinear control, estimation and identification, and process monitoring, diagnosis, and education. So what we're going to do here, we are mainly going to concentrate on the control design and the multivariable controller. However, we may not be able to do the adaptive and predictive controller due to the reasons of the corona thing that we have this year. Okay, so there are many things we can do here. So TE, which is the Tennessee Eastman, okay, abbreviation for that, process the simulation environment of a real chemical process. The TE process includes following units: an exothermic two-phase reactor. Okay, it's an exothermic of a two-phase reactor. What is two-phase? Liquid and vapor. A flash separator. So a flash separator, that means you're like flashing this liquid and it's like spraying something, and when you spray something, to lower pressure. It's like you're spraying with a high pressure to lower pressure. It just goes as a mist or as a vapor. So you have a separation of a gas and a liquid. Okay, it's called a flash separator. And then a reboil stripper. So you have a reboiler and a stripper. Okay, and then the stripper, that means you're stripping out gas that goes back to your reactor. So there are a total of 41 measured output variables. Okay, so there are 41 measured output variables. What do we mean by that? I'm measuring the flow rate. I'm measuring the temperature of the reactor. I'm measuring the level inside the reactor. I'm measuring the pressure inside the reactor. I'm measuring the flow rate of each of the input feeds. I'm also measuring the flow rate of the output of the compressor. I have also the measure of the power of the compressor. I have a measure of the flow rate of the purge. I have the measure of these process variables for the separator. I have the measurement of pressure, temperature, level, flow of the reboiler, of the stripper, and I have, of course, the measurement of the flow rate of the product. So these, if you count them, there will be 41 measured output variables. And I have 12 manipulated variables. 12 manipulated variables. So what do we have? Usually the manipulated variables are the ones that I can manipulate or change, that I use for control. So what do I have here? I have this valve. Usually this is present as valve. This is the manipulated variable. So I have 1, 2, and I have 3, 4, 5, 6, 7, 8, 9, 10, 11, and the stirrer could also be counted if you want as 12. Okay, we also have the compressor. Actually, if you can control the compressor, but I'm not sure if that is included within the system or not. So we have the 12 manipulated variables. The original benchmark was, of course, coded by Fortran. Now we have Simulink environment to work on. Okay, Simulink environment, which you already trained on to use. So what is the main control objectives? To maintain the measurement of the product rate and the composition as set points. The main objective is to have this process plant to work, to operate, and all the measurements are kept at its place, and we have a constant product and composition at the set points. So that means I'm going to give you the set points. And be careful while keeping all the other variables of temperature, pressure, the measure variables within the shutdown limits. So the system should not shut down. And shutdown limit, you're going to see that's like a straight line. As a person who's dead, sorry for that, but you're going to see that as a straight line, and which means that this is a shutdown limit. Okay, something like that doesn't move. Okay. Okay, the objective of this process is to develop certain techniques for the purpose of monitoring and control the T process benchmark. Following tasks need to be investigated in the project. Okay, so what you're going to do, study on the Tennessee Eastman Process benchmark as well as Simulink implementation. And you're going to control it. After you study it, you're going to control it. You're going to develop 3 control configurations for 1090, 9010, and the 5050. Of course, each one will also have several configurations. It could be 2 or 3, each specific one. I mean, 1090 will have like 2 or 3, the 5050 will have 2 or 3, and the 9010 will have 2 or 3. Control design is based on non-linear MPC. If you get to this, if possible, we will try to do it. And this is what I'm expecting the objective of this project to design the control system of the plant. And I would expect you to explain, sorry, that's not the distillation column process of the Tennessee Eastman process. You're going to draw the PNI diagram, okay, and so I'm going to correct this. So this is for the T Eastman process, and you're going to have identify what are the manipulated and control variables, the control configuration, first control configuration, the second control configurations, and the control loops. Why are you putting these control loops? And then you're going to talk about emergency and shutdown processes and safety processes, and you're going to mention the types of valves that you're using, the type of transmitters that you are using to measure here for those instruments, the PI, the TI, PI, LI. What are the types of those instruments? Okay, And I'm expecting also to tell me what are the standards that you have used. Okay, what are the standards that I have used, and what are the restrictions or constraints. Okay, so this is part of what you're trying to do. So the details of the project, you have 3 objectives: select and control the system configuration, specify the measurement system and the final control element, and select and tune the process controllers. Our 4th objective, the economical, safety, and environmental aspects. We are going to give you the numbers, and you should also consider the economics into your consideration. So this is an explanation of the project here. It tells you that what you're trying to do here, you're having a product. Okay, you're having a reaction that happens, and we already said that we have A, C, D, and E as inputs, and I'm going to show you this in a better way of representation in DONS, but these are the reactions that we have. Beautiful. So DONS and Vogel represented a complex control and optimization problem of Tennessee Eastman of industrial recycle reactor process. And this consists of an unstable system. It is unstable. Believe me, it's unstable. You're going to suffer. Sorry, I don't mean that, but it is unstable, and it's going to be not easy task. It's not an easy task, but I'm sure that you are engineers and you can do it. As always, my students, they prove that they always can do it. Okay, consisting of 4 units, we have an exothermic reactor, a flash separator, a revolt stripper, and a cycle compressor. So this is like a plant, and we are trying to design the control for the plant, control system. Depending on the current market need, the process was operated at a fixed production rate or maximum production rate on 3 different product grades. What are the product grades? 1090, 10G, 90% H. And 90% G, 10% H, 50% G, 50% H. And there are a number of disturbances. You need to test your system. After you do the control, you test it against the disturbances. And you also need to do some kind of set point tracking. So the gas reactants in the reactant where the unreactants undergo irreversible exothermic catalytic gas phase reaction. So this is the reaction, right? And because it's exothermic, that means I'm going to have the temperature is going to be increasing. Okay, why do I have a partial condenser? But because I want to recover the products, as we have said, that goes out from the reactor. And the stripper is to minimize the loss of any reactants, because we still have little sum of reactants. We do some kind of stripping to get the reactants back. And of course, the gas overhead from the stripper is combined with the compressed overhead from the separator and recycle back to the reactor. So that means that the gas that goes, the overhead gas from the stripper is combined with the gas that is compressed, that is coming from the separator, and then it goes to the reactor back again. So this is the problem that we have, and that is what you have here as a process, and that is for you to look at into details. Okay, what is the control objective? The control objective of this project, for this process, is to maintain the process variables at desired values. What are the process variables? Temperature, pressure, flow rate, and level. Key process operating condition within the equipment constraint. That means there are some operating conditions, there are some equipments that does not withstand a high temperature or a high pressure. So the equipment has a constraint of pressure and temperature, and that we call as an operating condition. Okay, we want to minimize the variability of product rate and product quality, so we are going to introduce the disturbances, expected disturbances, and when we introduce that, we want to see how does the product rate or the product quality change. Okay, does it change really a lot, or we are able to minimize that variability? And we also want to minimize the movement of the valves. Okay, minimize the movement of the valves. And talking about the movement of the valves, to minimize is really important, because you could have a good process that is controlled, but the valve is is opening and closing, opening and closing, opening and closing. Okay, so the movement of the valves, if it is crazy going up and down, is also not it's not good, because it's going to destroy the valve. Recover smoothly from disturbances, we already mentioned that. Okay, so it should recover. So minimize the variability of the product rate and recovers from the disturbances for the process variables. And we also need to do some kind of set point tracking, which is part of the testing process that you're going to do. So you're asked to do 2 alternative processes. Here I'm going to say that you need to do 3 alternative proposals for as 2 alternative proposals for all the different conditions that we have, which is 1090 GH and 9010 and 5050. Okay, so that is the challenge that you have. You're going to make some decisions for the control structure. You're going to also talk about the startup procedure, part of the system. You're going to tune your controllers and how you're going to decide on tuning. You're going to design controllers to reject the disturbances, and stabilizing controllers could be possible, and do a multi-layered approach if you need to. Okay, so this is what you're going to do. If we get a chance, we're also going to do some kind of optimization scheme and safety instrumentation system. I mean, if we are not able to do it online, at least we're going to explain it. We are going to show what could be the SIS system, and I'm asking only for one scenario, worst scenario for one emergency shutdown system. Okay, so what are the modes that we have? We have 50-50, 1090, 90-10, okay, which are of different production rate, and we have also that with a maximum production rate that is different from those production rate. So these are the modes of operation that we have. So we have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. You're going to have a control configuration which is best reached to that, and then that, and for the rest. Okay, so what do we have? These are the information that I have, the physical properties. You may need them. You may get the idea of which one has more heat of vaporization. So that is a good information for us. If I'm increasing the temperature, what will be most affected by temperature and what will be less affected. So there is some information that you can get again out from here. What are the process manipulated variables? These are my process manipulated variables. XMV1 is D, XMV2 is E. X is just for a variable, MV is manipulated variable. So XMV3 is the feed rate of A, XMV4 is feed of A and C, XMV5 is the compressor recycle value, and so on. So if I want the reactor cooling water flow, it is the manipulated variable number 10. These base values are already introduced within your Simulink system, already introduced. Great. Now I also want to tell you that we have 42 measurements, and the 42 measurements are represented as X measured, MEAS 1, X measured 2. So what is the flow rate of A? It is X measured 1. What is the flow rate of 2? It is X measured 2. What is the flow rate of E? It's X measured 3. What is the flow rate of A and C? It's X measured 4, and so on. Okay, so this is the way of looking at all the measured process variables that you have at the system. Okay, all of them, and here they are distributed for you as those related to the process measurement, and those related to the reactor feed analysis are kept separate here, and those for the purge gas analysis are these measured variables, and those for product analysis are kept here. Okay, and this just makes it simpler for you. What about the process constraints? Okay, and this is where you have shutdown limits. Okay, for example, reactor pressure, it's fine to go to low pressure, but if you go high, the maximum you can go is 2895, and if you go to 3000, the system is going to shut down. Okay, it's going to shut down. The simulation, the Simulink file is going to shut down. I don't mean shut down to close. It will show you a straight horizontal line that it shut down the system or the process or the plant. Okay, so the reactor level within the reactor, 50% is the minimum, 100% definitely is full, is the maximum. Okay, so shutdown limit if it's 24 meter cube. Reactor temperature, if you go low, it's fine, but if you go higher than 150, it's problem. That's the normal operation limit. But if you reach 175 degrees centigrade, it's going to shut down. What about the product separator level? 30%, 200%, 12 meter cube is a shutdown limit, and so on. So these are the shutdown limits that you have. Now, after what I have explained, I'm going to go to Don and Jones, but before I do this, I need to show you the Simulink file. Okay, I need to show you the Simulink file that you're going to work on. And here, looking at the Simulink file, I know it's the first time you look at this thing, but so I'm just showing you up and down, so how that will look like. So this, you have this file. Okay, so you have this file. And what do I have here? What do I have here in this file? Let me look at. All my model is sitting here in the S function. Okay, so my model of this whole plant is here. So what I do have output for my model, my X measured. So what do I have X measured? I have all the X measures that I need. Okay, what do I mean by that? Just a sample of it. X measure 6, which is the feed, the reaction feed. X measure 7 is the reaction pressure. X measure 8, which is reaction level. X measure 9 is the reaction temperature. Where did I get those from? I got it from the output of this Dmux. So I have all my measurement variables taken out of this S function, the model of the plant, and you can count them. This is X measured 1. This is X measured 2. The terminator is just saying that I don't want to use this measured. Just keep it as a sensor, and I don't want to use it. Okay, so I have X measure 1, X measure 2, X measure 3, X measure 4, 5, 6, 7. And if you see 7, this is number 7. You can see how it shows here. And if you see 8, you can see that it goes like that. And if you see 9, so this was done for you just to look at it. And then 10, 10, I cannot get 10, okay, so I cannot get to it, but you just need to move this thing away from my site so I can tell you which one is 10. Oh, there's more than one. Okay, there's more than 2. Okay, come on. Okay, so I forgot the numbers now. For I don't know what 9 or 10, so I just forgot. Okay, so this is 9. Okay, this is 9, so there's 9, 10, 11, 12, and if you count them, you find 42. Okay, so that is the measured, that's the X measured. What about the manipulated variables? These are my manipulated variables, and these are the base values of the manipulated variables. So the manipulated variable 1, manipulated variable 2, manipulated variable 3, manipulated variable 4, and so on. What are the manipulated variables? If you can just recall, XMV, 1 is the feed flow rate of the D. So this is the feed flow rate of D. And you can see the value 63.053. It is the base value 63.053. If we go, for example, to manipulated variable of which one here, I would say the cooling water. The cooling water for the reactor. Okay, it's XMV10, which is 41.106. And it tells you here that's number 10, 41.106. Of course, what you're trying, for example, you're measuring the reactor temperature. Okay, so you're measuring the reactor temperature, which is X measured 9, and you enter this to a comparator. Okay, where you put the set point, and you have the error, and the error will enter my PID controller, and then my PID controller is going to take action on what? On the manipulated variable. So it will manipulate the cooling water to get the required reaction temperature. So that is the idea of what you're trying to do here. Beautiful. So what do you have? What do you have as a system here? So what I have here, I'm going to start with DONS mainly because it's the main thing of the project that you have, and this is what you have from DONS. So this paper describes a model of the industrial chemical process, and these are the reactions. A plus C plus D gives you G, which is a liquid. A plus C plus E, which is H, which is also a liquid. Of course, this will be a liquid and a vapor. You will have two phases, and this is why you have the liquid is collected inside the reactor, so you have a level. And the process has what? it has two byproducts, and because of those byproducts, I want to get, I don't like the byproducts, right? I want my product G, I want my product H. Where is the byproduct? Okay, I want to see them. They're here. A plus A reacts to give me F, and 3D gives me 2F. These two byproducts are not required. They are not favorable. Okay. So two additional byproduct reactions also occur. The process has 12 valves, as we said, 12 manipulated variables for manipulation, and 41 measurement available for monitoring and control. Great. So these are the reactions that I have. I have 4 reactions, 2 products and 2 byproducts, and all of them are irreversible. You need to read more about it. Like, for example, it's written here for you: the reaction to produce G has a higher activation energy, resulting in more sensitivity to temperature. So G, it has a higher activation energy, which means G is more sensitive to temperature. So I think you heard that, right? So you need to consider those properties so that you can decide on your control system. The reactions are approximately first order with respect to the reactant concentration. So you can consider that as a first order. That is the plant. We already had explained the plant. So what do we have? These are the 6 modes that we were talking about. Okay, the 6 modes that you have. The main first 3 modes are the most important part that you need to get. We will not do 4, 5, and 6 because this is like part of the optimization scheme. If we have time, we will work on it, but we need to concentrate only on 1, 2, and 3. Okay, the first three modes. This is the information, the data that you have of the heat and material balance, of all the data of temperature, pressure, heat, liquid volume, reaction, cooling water, all of the data you have. Okay, and the physical properties of the data, of the activation energy, the heat capacity, and so on. What are your control objectives? I already mentioned the control objectives. I have taken them exactly from this paper. What are the constraints? I already told you about the constraints in table 6 that shows the shutdown limits. Okay. And of course, for every flow rate, there is a certain valve, and the valve goes from 0 to 10%. And depending on that diameter of the valve and what pressure of head pressure pushing or from the gas pressure is pushing that gas or liquid, you have a low limit and a maximum limit. You may need to put, please hear this, you may need to put a saturation for all the valves to say that it is from 0 to 100%. Okay, so be careful with that. Be careful with that. Okay, so this is the base case value. Base case value which tells you that it is 63.053%. Okay, so this is the base case value. Each of the manipulated variable by setting the corresponding xm variable to a value between 0 and 100. Okay, I'm just mentioning this again. The ranges of all xm variables are 0 to 100. Why do I mention this? Because sometimes you forget and you manipulate the xmv to 110, and then you tell me, oh, I got a good response of a temperature, but you never can get an xmv of 110. Okay, so please consider that into your consideration. And these are the x measured variables, and again the base case values with the units. So these are the measured, and all those are in Simulink, as I have said. And this is the table 6, which shows the limits of low and high limits and the shutdown limits that I have. So I have low and high limits, and I have shutdown limits. These are constraints, and you need to mention that in the project. Of course, you have constraints. So how you're going to test your system? After you finish your control, you're going to test your system. Testing your system is like what? Saying that, well, I'm going to make a step change in the production rate change, which is the flow rate of the product, okay, minus 15%. And we are just giving you the numbers to get the idea of what you're going to do. The product mix change, I'm going to do a step change from 50-50 to 40-60. The reactor pressure, I'm going to make a step change of minus 60, like 2705 to 2605. And if you make these step changes, this new set point changes, will your control system be able to do this or not? And please consider that similar set point changes can be made with other operating modes. To realize the full effect of these set point changes, if you want to see the effect of these set point changes and if you are successful or not, we suggest a simulation time of 24 to 48 hours. So please go to 48 hours. Sometimes it's enough 24 hours and you can get everything ready in front of you, okay? Okay, so what I'm saying that if 24 hours is good enough, it's good enough, okay? Feed flow variability. Now we need to control this variability of this feed flow rate. The valves should not go like that, okay? Like that, like that, like that. It shouldn't go up and down in this form. Okay, we also have some kind of disturbances in our process. We have disturbances, and these are the name of the disturbances. Like there is a disturbance, the temperature of the feed of D changed. And what was this kind of disturbance? It was a step disturbance. Of course, you're not going to make a step change. You're going only to change that disturbance. Okay, you're going to change that disturbance. And all the disturbances are kept as 0 because we are dealing like with a deviation variable. So you're going to change that 0 to a certain value like 0.1 or 0.2, depending on what? Depending on the type of the stream. If you're talking about flow rate, you're going to talk about 0.1. If you're talking about temperature, you may talk about 1 degrees centigrade. Okay, if you're talking about pressure, it could be different, and so on. There are many disturbances. Some of them are step, some of them are random. It's like just it's like imitating of what is happening in the real plant. And the real plant, you could have some conversions that are random. You don't know how it happens. It could be a slow drift because of kinetics, because of the catalyst. It could be a sticking, and a sticking, that means the valve is getting sticky, okay, in that sense. And so all those are possible. Disturbances 14 to 20 should be used in conjunction with other disturbances. So don't do 14, 20 by its own. If you're going to do 14 plus number 1, 14 plus number 2, okay, if you're going to do this. And again, simulation time of 24 to 28 hours. We would like you to do as much as testing for the disturbances that we have as much as we can, and we would like to take like 3 step inputs, 3 random variables, and then one sticking and 1 unknown in conjunction with the others. Okay, so what I want you to do to concentrate more on, I already it's not me, I'm just basing on the paper. The mode 1 has 4 set point changes suggested, so this is for you. We will also suggest for you to do 4 load disturbances: step change in IDV1, step change in IDV4, random variation IDV8, and then simultaneous random variation and sticking valve ID12 with one of them and ID15 with one of those. Okay, so we need only to do this. Okay, you need to do only these, just to make it simple for you. You have process operating cost, so you can calculate how much you are operating. Because of your control system, you will have better operating cost or a worse operating cost. Total operating cost is the purge cost into purge rate, because you're losing your feed. My feed, which is the inventory, if I purge them, I'm losing money. Product stream cost into product rate, so I'm also producing that. Compressor cost, a compressor is very expensive, it is very expensive, so into the compressor work. Steam cost, steam is also very costly, into the stream rate. Okay, so you need to calculate this. So I just want to mention here about the product stream cost. It's mainly what is used to cool down and mainly for the system, because product rate actually it will be a cost if you want to store it, right? So here it mentions that if you want to produce this, how much it will cost. Okay, so it has an idea of just a whole number there. Okay, great. So this is what you need to do. This is what you have, and that is just explaining the system that you have. So now what you need to do, we need to go and see the system. So I will give you something called TE MATLAB. Okay, this is the file that you have. you will double click on that file, and you're going to see the papers, DONS, which is the most important paper for this project. You have McAvoy as well, and you have some other papers that you can rely on. And I'm going to go to the other papers, by the way, now. So under TE MATLAB, you have all the files. This is the file. This is the file that you're going to start with. Since we are talking about SLX, so you're going to go to a file of an SLX file of the new version. So what we have MATLAB. This is MATLAB. So what you need to do first, you need to select. You need to select that folder. Okay. So I have it also stored under something called stuff here. So I have it stored. I just want to show that to you. Okay. So if you go to T1 stuff, so you see all the files here. So you need to go to the folder that contains those files. How to do this? You double click, on that, and you go to your file T1 stuff. So all the MATLAB and Simulink files are here. I'm going to put select folder. I selected it, and all the files will appear here. And then you're going to double click here. You're going to double click tv5sim.mdl, and when you double click it, you will have this file appearing for you. Okay, so it will appear to you. Now if you want to run the system, let me see, does it run or not? And if it doesn't run, I will tell you why, and I'll tell you then how to fix this this bug. Or it's not a bug, right? It's just something that we could have missed here. So I already clicked on the run. Okay, as you can see, it's about 2% here, and in a moment it's compiling, it's running. Oh my god, I have an error. And what does it say? Cannot find an exact case sensitive match for TES function. What does that mean? It means that if you go to the file here, it is all caps, right? It's caps, TES function.m. So which means that if I just change this to to caps and apply this, you're going to see that it's working. And let me run it again and see that if it's working or not. Oh, beautiful, it's working. Okay, so now it's working and we are very happy. If you want to look at how does the reactor pressure react or changes, we can see that just by double clicking on it, and by double clicking on it, that is my reaction pressure. Okay, reaction pressure. But this looks like a steady state value that is based on all the base values. Any step change will change the whole life of this plant. So we need to keep it with control. Okay, so what do we have? We said that we're going to take just one example, and now you need to start doing the control configuration, right? Do it on paper, and then whatever you suggest doing in paper, you're going to reflect that. Here. So just take an example. How to include my PID. How to include my PID control system. So the first thing to have my PID control system, if you remember that you need to go to continuous, and you're going to have the PID controller. So when you have the PID controller in here, okay, where is my PID controller? Yep, it's there. So what do we have? We need also a comparator, by the way. Okay, we need a comparator. So where do you find it? You find it through math operations, and that is where you find a comparator. So you're going to have the error getting in. So what is the error? It is the measured minus the set point, right? So it's like I'm taking the measure. Oh, it's not that. It's not that. Oh, I'm trying to take the measure of the reactor temperature. So it's the measured minus the set point. Okay. So this is what we have here. Apply. So I have a plus and minus, and I need a constant value which goes from the sources, and taking a source here, and I'll also take from the sink a scope so that I can have my figure later. So what do I have here? I have my error. Okay, so I have the error, it will enter here. So this is like t set point, right? T set point. What is t set point? If I want to control it at the normal operating conditions, and the normal operating conditions, if you go to the PDF file and you search for the normal operating conditions or the set point values, okay, the set point values for the temperature. So if you see the reactor temperature here says 150 degrees, right? 150 degrees. So I'll say that this is 150 degrees. Apply, okay, and what's going to be the output? The output of the PID controller tries to go to the final control element, and in this case what I'm trying to do in the system here, if you just can recall, okay, what I'm trying to do here is that I have the plant, okay, this is like my plant here, and in this plant I have the temperature of the reactor, and the temperature of the reactor, if I want to control this, I measure the temperature here, and by measuring the temperature, how to change the temperature inside the reactor, I cool down the system. You can see the cooling water going like that, and it goes inside here, and it goes inside here, and then it goes out. So it's cooling. So I'm using the cooling water to cool the system, and this is the way of how we are trying to control the temperature. So how to control the temperature? I need to go to the cooling water. What is the cooling water? Okay, so let me go back again. What is the cooling water? Let me look at the XMVs. The XMVs, where's the cooling water? Reactor cooling water flow is XMV10. Okay, so I just showed that to you. That's XMV10. So here's XMV10. Delete XMV10 and take that into sorry for that, where's, oh my god, I stuffed things up. Okay, so I need to go little up here and down there. Okay, so that is my output. I'll try to take this thing here to up. Yes, is there. So now I'm trying to do what? I'm trying to control my temperature. Okay, and this is the output, and the output is the valve. Okay, so I need another scope to see how does the valve look like, and I also want to look at my I already have a scope for, okay, I already have a scope for the reaction temperature, which is here. Okay, so I don't need this. Okay, so, and to be also, this is the cooling water feed. Okay, flow rate. It's good to write everything, because when it gets really messy, you're going to forget everything. I don't mean Messi and Ronaldo, by the way. Okay, so I mean Messi. So what I need to do here is just run the system. It's compiling, it's running, and it's finished. And what happened? I just want to look at my reaction temperature. Is it under control? Whoa, it looks like it's under control, and that's great. The answer is what? Is no, it is not under control. The temperature went above 50. The valve tried to put it down, but then it shooted up, and when it shooted up, it hit the shutdown limits and went down to shut down. Okay, but let me tell you something. It did not hit the shutdown limit of the temperature. There is something else that hit the shutdown limit, which made it, because as you can see, this is not the shutdown limit. So it could be that the pressure went out of control. It was the pressure. As you can see, it was the pressure that made it shoot out. It went over 3,700. And if you go back and look at the shutdown limits of the pressure, so that is the reactor pressure, 3,000. It went over 3,000, definitely. It went over 3,500, and that's why it just shut down. Okay, so this is like showing it's shut down. And actually, if you want to look at what happened to my valve, what it was trying to do. Well, oh my god, my valve is minus 30. Did you see our mistake here? We cannot have minus 30. We cannot have minus 30. We need a saturation between 0 and 100. And this means that you're going to go again to your simulation library browser. You will take the saturation and you're going to add the saturation here. And now after you had add saturation, you're going to tell it, please, it is going from 0 to the upper limit, which is 100. Okay, and now I'm going to run it again and see what will happen. Okay, what happened to my cooling water? It looks like it tried to do something, but it went down again to 0. But maybe that is not 0, that is a shutdown limit. And if you go to reactor temperature, again, it looks like it's shutting down as well. And if you go back, okay, if you go back to the reaction temperature, oh, I already did that. Okay, what else did I? The reaction pressure, you're going to see that it's also shoot over 3000. Okay, by the way, is there anything to do with the KC, if it is reverse acting or it is direct acting? It could be the reason that it's reverse acting or direct acting. I don't know. I'm just having something in my mind that is going on that tells me that it is that we should change the values here. And looking on of what I have done, it looks like there was something like a temperature control here. Let me the pressure also went up. So we need to look at the KC values and the tau I values. What I'm trying to say here, if you increase cooling rate, what happens to the temperature? If you increase the cooling rate, the temperature goes down. So they are opposite. And since they're opposite, so it's like reverse acting. And this is why you need to work more on playing with these terms, okay? On the KC and the tau I values. Well, you don't start by this way, by the way, okay? What I have mentioned here is not correct. Oh my god, what's that? Okay, sorry for this. And it just looks like how crazy is this, right? It's out of control, and then it shut down here. It shut down. And why did it shut down? Again, there was some kind of a control, but the pressure still goes to 3000 and it goes down. There are reasons of why this is happening. The reasons are as follows. Okay, the first thing you need to do in your project is to consider the inventories. Okay, that means try to put a feed controller on all of your inventories. After you do this and you control your inventories, then second thing, you need to go to the operating conditions of your system, which is the temperature here, which is the level here, which is the level here, which is the level of the separator, which is the level here at your stripper. Number 3 that you're going to do is to go to your production rate. Okay, so take these stages as you go on, because these stages will help you to do a better control. And by the way, if you go to the file that I have supplied to you, if you go to the file, there is an introduction to Plantwide control, or this file is good, Plantwide control, a review and a new procedure. It's really good. Process dynamics and control for CBOG. Go to chapter, I think number 10, which is plant design control. It will tell you that you need to start with the inventory and so on. And if you double click on this, and if you go to chapter 10, I'm not sure if it's chapter 10, I just said it. Okay. Okay, if you go to chapter 10, and that is chapter 11, where is 10, please? Okay, so if you go to chapter 10, okay, so here's chapter 10, overview of control system design. I'm right. So steps in control system design. Okay, so how do you do those steps? It explains the steps for you. It tells you that control is important for what? It's important for safety, to not to exceed the environmental regulations, which are important to our whole life and all this life that we're living with, the plants, the animals, and us and everyone, right? It's not just a regulation for a regulation. Or Control is also important for production rate, for economic reasons, that we need to have more profit and to have a more stable plant operation. And the steps, remember the steps: you choose the controlled, manipulated, and measured variables. You choose the control strategy and control structure. You specify the controller settings. So you're going to go through all this. What are my control what are the process variables that I want to control? What are the manipulated variables? I'm trying to map this manipulated variable with a control variable. So you're going to select or link which manipulated variable is going to use for that measured or operated variable. And when you do this, if you remember, that you can use RGA analysis. Oh my God, you want me to do RGA analysis? If you go to McAvoy, this guy, he did a great job. And actually, what he did, like, this is the plant. These are just the same process variables. These are the same manipulated and control variables. Actually, McAvoy is showing you that he had done control. So you could have a look of the control system of McAvoy. Okay, so please have a look. You see a feedback loop for all the inventories, and then he starts on with what's inside there. If you can see that he has a temperature controller as well there. So look at it. It is beautiful for you to look at. And actually, you will see that McAvoy, he had done an RG analysis. And you can use this RG analysis of what he have done and the pairing of the manipulated variable and the control variable. It's beautiful. You just can't use it out of the shelf, right? So the RG analysis here, you need to know how it is done and you need to explain it. Okay, so you need really to know how this is done. And if you're going to run it, it's going to be great. Okay, so that is the RGA analysis that is done. So you can have a look at this. So you have Downs and you have McAvoy as well. And you have the process dynamics and control book, in which you already have the textbook bought by you. So you're going to see the stages that we need to consider when we are dealing with the control design process. And here's just an example of the control design process. I'm not going to go through the system here. It is different. A part of what you're going to do, you can calculate the number of degree freedom. A degree freedom is simple, telling that how many process variables I have and how many. It's not the degree of freedom of a system. I'm talking about now degree of freedom of my model here. So if you look at how many process variables I have and how many manipulated variables I have, you're going to see that you may have a problem that in your degree of freedom. Okay, it's like that means how many can be independently controlled, and usually you will not have enough to independently control every part. Okay, so that is that part, and so on. So what do you have? You have this system here. Go on and start your project. That is the challenge that you have. And then what you're going to do, you're going to do some kind of set point tracking. Okay, set point tracking, that means as you need to change the set point. You need to change some set points to see if it's tracking or not. You're going to do a step change at the set point. And these are the disturbances sitting for you, and we already identified the 4 disturbances that you need to test your system with. That's all for your project. You have a challenge to work on. I'm going to show you just a final paper, Lyman and Gergikis, and they also did some kind of a control system. So this is what they have done. This is another control system, temperature controller, right? And also a flow controller, but he is having some kind of the analyzer. He's using the analyzer to be cascaded of the flow controller. So it has some kind of configuration on the purge and also on the product of X, G, and H, and on the reboiler, which is also cascaded of the temperature of the flow controller. It has a different way of looking at things. It's beautiful to look at what people have done, and this is what he went through. He also decided that that you're going to have total operating costs different for the different control structures, and this is what I want you to show. It's like you're going to show me that for the different modes that we have and the different control structure that you're suggesting, the one which has less operating cost is the one that you're going to select. Okay, so please consider this, please consider that, because it will help you on the selection process. Okay, stability is part of it, but the selection process is also start of it. This is a good way of saying that the product flow rate of how it's varying is not really much varying with time, which is really good. And this is how the pressure was under control. Structure 1, 2, 3, 4, there are different structures, and in each structure the variations are high or low, and you can see how the variations for all structure, for the production flow rate and for the flow rate and for the reactor pressure and so on. So beautiful how we can see things, right? And this is how GNH for the 50-50, I think so that was a set point change, a closed loop of a product ratio to set point change. Yeah, there was a set point change for control structure 2, so he shifted from 1 to 2, and this is what you're getting, and that's how the reactor pressure, and these are the results. It's very beautiful to look at it because it gives you of how you're going to represent all of your work in that plan design project, plan design report. All the best, and this is your project, and I'm sure that you can do great. I'm happy to explain any more inquiries that you have. All the best. I think so now you can depend on yourself. Work in groups, but be careful of the corona thing, so try to work everyone from home through Microsoft Teams or Zoom to be able to work in groups. Thank you very much. All the best, and I wish you a very great and a pleasant day, week, and month, and a semester. It's going to be tough, but it's going to be worth doing it. You're going to learn a lot. You're going to learn a lot. You'll feel as an engineer in this course. Thank you very much. See you. This is Dr. Bassam Al-Hamad, and watching forward to look and hear from you again. مع السلامة.